In this video, we're going to go through example 8.5. You're welcome to watch the video and hear my explanations, or just download the completed notes down from Moodle. So if you want to watch the video, feel free to follow along. What we're looking at in this video is the power that it takes for a pump, really in this case the pressure that it takes for a pump to move water down into this large tank at a given flow rate. So what we know about the system, we have a pump, we have a reservoir that is 10 meters deep, and we're pumping at a volume here of 0.01 meters cubed per second. The basic equation that we're going to be looking at is here, and we're going to be looking at two different types of head loss. The head loss that we're looking at is, of course, major losses, which is flow down the pipe itself, and minor losses, which are caused by things that are not straight sections of pipe. So when we're looking at major losses, we have flow down the straight pipe. And minor losses, the only minor loss in this case would be flow out of the exit. The models that we can have for these two types of losses, for major losses, this is going to be the friction coefficient. We're not sure yet if this is laminar or turbulent flow, but it doesn't actually matter because this general equation is true for either. Just the value of this friction coefficient F is going to be what changes if we have laminar or if we have turbulent flow. Then the minor losses, the general model that we have is K times the average velocity over 2. You make that a little bit more clear. Okay, so these are the two models that we're going to be looking at. We'll draw our control volume to encompass both the pipe and the reservoir. So it's the dashed line in the figure. So it goes right up to the pump outlet. So we're asking, what pressure do we need at control surface 1 in order to cause this flow? At the pump, we have the pressure P pump. We don't actually know what that is. We have a height, which we'll define as 0 meters, and a velocity, which is the velocity of the flow, which is simply equal to Q divided by the area. At control surface 2, which again is at the top of the reservoir, we have atmospheric pressure, which is 0 gauge pressure. We have a height of 10 meters and a velocity of approximately 0 meters per second. Again, that's the velocity in the reservoir. That would be the velocity up in the reservoir at control surface 2. So how fast is it filling? Well, it's going to be relatively small. When we look at our head loss equation, we can break down the head loss into these two different components, HL and HLM, the major and minor losses. And we essentially only have these terms remain after we fill in the head loss equation. We can separate the head loss into the models that we have for major losses, right here on the left, and the model that we have for minor losses here on the right. The minor loss coefficient K, we can find K for a square-edged pipe entrance. This is in table 8.2 in our book, and we can look up a value of K. K is about 0.5, right? And that's just a unitless constant. When we take this equation and solve for the pump pressure, we're just solving algebraically. We would get this equation here. We can find, now we know density, we know gravity, we know D, the depth. We don't know F yet. We know L, D, we don't know V. So we know most of these things, but not quite all. So the next thing that we have to find is the velocity. We can find the velocity simply from the average velocity equals the flow rate divided by the area. So this is 0.01 meters cubed per second. That's the flow rate divided by the area, pi r squared. So that's pi times our pipe, which is 75 times 10 to the minus 3 meters, but that's the diameter, so we'll divide it by 2 and then square it. This gives us a velocity of 2.26 meters per second. So this is the average velocity that we need. We can then take that average velocity and figure out what's happening with our flow as far as the Reynolds number. So we look at the Reynolds number that equals the density, 1,000 kilograms per meter cubed, times this average velocity, 2.26 meters per second, times the diameter, 75 times 10 to the minus 3 meters. Remember, for Reynolds number, what I have labeled as D here, the pipe diameter, that's typically you can consider it's the characteristic length of the problem, which is the most important length in the flow system. There's not really a hard and fast rule, but typically if you're flowing over something, it's the length, the size of that object. If you're flowing inside of something, it's the size of the opening, so the diameter of the pipe. Then our viscosity, we could look up for water. At room temperature, it's about 1 times 10 to the minus 3 kilograms per meter second. This gives us a Reynolds number of 1.7 times 10 to the 5, which tells us that this is turbulent flow. Right, the cutoff for pipe flow is about 2,500, 2,300. So we're certainly above that. We're 1 times 10 to the 5, so we're turbulent. In turbulent flow, our alpha value is about 1.05. It varies a little bit depending on Reynolds number. This is approximately 1.05. For a smooth pipe, we don't know what the surface roughness is exactly, but if the pipe is smooth, we get this nice simple equation for friction factor. If the pipe is not smooth, there's our other correlations as well as the Moody chart, which can help us find the friction factor F. If we use this correlation, we can find a friction factor of about 0.0156. So that gives us most of the things that we need. Now we just need to find the pressure for our pump. So what we're finding is solving for P pump. We now have all of the different components to that equation. We have gravity, the height. This is the friction factor that we just calculated, L over D times V squared over 2. So those are major losses. Our minor losses from the flow from the pipe into the tank. And then here we have the change in kinetic energy, alpha times V squared over 2. When we put all of these things together, we get a pressure in our pump of 149.7 times 10 to the 3, and then a big kind of jumble of units. So if we go through here and all of the units that we have, all of these terms inside the parenthesis have units of meters squared per second squared. So we have kilograms per meter cubed, meters squared per second squared, and this will simplify to newtons per meter squared or pascals. So the pressure that we need coming out of the pump is 150 kilopascals. That would be the pressure that's needed to drive this flow, to drive water into that tank at a flow rate of 0.01 meters cubed per second. So hopefully you find this helpful. Again, the book goes through this as well, so if you want to check back in example 8.5 how the book does it. Otherwise, feel free to reach out with any questions if you have them. Thanks.